Hello, and welcome to 8slides.com. Today, we're demystifying one of the most exciting and impactful technologies of our time, neural networks. Often heard in discussions about AI, these systems are fundamentally changing how computers think and interact with the world. We'll explore how they take inspiration from our own brains to recognize patterns, make decisions, and drive innovations like self-driving cars and personalized recommendations. Over the next 8 slides, we'll break down their core components, understand their learning process, and see how they're used every day. Let's start by understanding their fundamental inspiration. The foundational idea behind neural networks comes directly from biology. Our brains are packed with billions of neurons, each a tiny processor. A biological neuron receives signals, processes them, and if the combined signal is strong enough, it fires, sending its own signal to other neurons. Artificial neurons, or nodes, operate on a similar principle. They take multiple numerical inputs, each weighted by its importance. These weighted inputs are summed up, an offset called bias is added, and then passed through an activation function. This function determines if the neuron fires, sending a signal to the next layer. It's this nonlinear activation that allows networks to learn intricate, non-obvious relationships in data. A neural network isn't just a collection of neurons, it's a structured system of layers. Data first enters through the input layer, where each neuron corresponds to a piece of information from our dataset, like a pixel in an image or a word in a sentence. This raw data then flows into one or more hidden layers. These are where the magic truly happens. Neurons in hidden layers process the incoming signals, applying their learned weights and activation functions to extract progressively more complex patterns. For example, early hidden layers might detect edges in an image, while deeper ones identify shapes or even entire objects. Finally, the output layer provides the network's answer or prediction. The number of output neurons depends on the problem, whether it's classifying an email as spam or predicting a stock price. The key to learning lies in adjusting the strength of the connections, the weights, between these layers. A neural network's intelligence isn't innate. It's painstakingly learned through a process called training. Imagine teaching a child to identify animals. You show them a picture of a cat, and they might say, dog. You correct them, saying, no, that's a cat. The network learns similarly. First, during forward propagation, input data, like an image, passes through the network to generate a prediction. Then, the network's prediction is compared to the actual correct answer, revealing an error. This error is crucial. It's then sent backwards through the network in a process called backpropagation. This allows the network to figure out which internal connections, or weights, contributed most to the mistake. Finally, those weights are slightly adjusted to reduce the error for the next time it sees a similar input. This cycle repeats millions of times with vast amounts of data, gradually honing the network's accuracy until it can reliably identify new, unseen cats. Neural networks are not just theoretical concepts. They are the unseen engines driving many of the smart technologies we use daily. When your smartphone unlocks with your face, that's a neural network performing complex image recognition. When you ask your smart speaker a question, speech recognition and natural language processing, both powered by NNs, are at work. Ever wonder how Netflix knows exactly what movie to suggest next, or how Amazon recommends products you actually want? That's sophisticated recommendation systems leveraging NNs to understand your preferences. They're also crucial for cutting-edge applications like autonomous vehicles, enabling them to see and react to their environment, and even for detecting fraudulent financial transactions. From convenience to critical infrastructure, neural networks are reshaping our digital and physical world. Just like there are different types of tools for different jobs, there are various architectures of neural networks, each optimized for specific data types and challenges. The most basic is the feed-forward neural network, where information flows in one direction, useful for straightforward classification. For tasks involving images, convolutional neural networks, or CNNs, are the kings. They excel at automatically identifying visual features, making them perfect for recognizing faces or objects. When dealing with sequences like spoken language or text, recurrent neural networks, or RNNs, come into play. They have a form of memory, allowing them to understand context over time. And for groundbreaking advancements in natural language processing, we now have transformers, which use an attention mechanism to process entire sequences at once, powering the large language models you've heard so much about. Each type brings unique strengths to the AI landscape. While neural networks offer incredible power, they also come with significant challenges. Firstly, they are incredibly data-hungry, requiring vast amounts of high-quality, labeled data to learn effectively. This data can be expensive and time-consuming to acquire, and if it's biased, the network will learn and perpetuate those biases. Secondly, training large networks demands immense computational power and energy, which isn't always accessible. Perhaps the most critical challenge is the black box problem. It's incredibly difficult to understand why a complex network makes a specific decision. This lack of explainability is a major hurdle in sensitive areas like medicine or finance, where transparency is vital. Networks can also overfit, becoming too specialized to their training data and failing on new examples. Addressing these limitations is an active area of research as we strive to build more robust, fair, and understandable AI. We've covered a lot today, demystifying neural networks from their biological inspiration to their incredible real-world applications. The key points to remember are that these systems mimic our brain's neurons, learn by repeatedly adjusting their internal connections based on data, and are the driving force behind most of the cutting-edge AI you encounter. While challenges like data dependency and explainability persist, research is continuously pushing the boundaries, making these systems even more powerful, efficient, and transparent. The world of AI and neural networks is dynamic and fascinating, with endless opportunities for discovery. For more accessible breakdowns of complex tech topics, be sure to visit 8slides.com. And don't forget to subscribe to our YouTube channel for visual presentations that make learning technology simple and engaging. Thank you for joining us.